Welcome back, and first point, which is representation of noise. So, as we said, noise can be treated as a random voltage or current being produced by certain random physical phenomena, like the random fluctuation in the electron trajectory induced by thermal fluctuation, and we can represent this as a time domain signal V t, right. So, although noise is not really a signal, it is just a random voltage fluctuation, we can treat it as a time domain signal V t, and we can define the power delivered by this noise signal to a 1 ohm resistor. If we talk about instantaneous value of V t being random, it is going to be almost symmetric across the 0 point. So, if we sample V t for long enough duration, sum of all these samples sigma V t I for all i's for a very long duration, we will get something close to 0, because these positive and negative fluctuations will add up to 0 if we sum them up for long time. That is the characteristics of a truly random signal. So, if I talk about the amplitude distribution, it may be something like a Gaussian amplitude distribution, where there is an equal probability of finding an amplitude V p as minus V p. So, on an average, the summed value of all the samples over a long period will be 0, close to 0. That is the characteristics of a random noise signal, voltage or current noise. But a more meaningful quantity, rather than defining the average or the mean, which is 0, the more meaningful quantity is the power delivered to a circuit component, and we can define the or quantify the noise source as in terms of the power delivered to say a 1 ohm resistor. That is a more convenient way of defining the noise. So, what do we say, how do we find out the power delivered by the signal noise signal V t to a 1 ohm load? So, we can write down V t square upon R, which is in this case 1 ohm, and integrate it over a sufficiently long duration divided by T, and this gives us the definition of power. So, if I say call it V n square and define the R as just a 1 ohm resistor, then this value is nothing but the mean square value of the signal V t, V n t. So, this is something like the mean square value of the noise signal V n t. So, we can represent the noise source in terms of its mean square, because it represents the power delivered to an effective 1 ohm load. So, it is an imaginary load we are assuming or we are defining, and we are quantifying this V t or the noise source V n t in terms of the power it delivers to this 1 ohm load. This is just a way, a convenient way of representing or defining noise. Now, what happens if you have say multiple noise sources? Suppose I have two noise sources in series, V n 1 t and V n 2 t, and we want to find out what is the equivalent noise power delivered to this load. Recall that if you look at the symbol of the noise, we do not put a plus or minus like we do with DC sources or an AC source. We put a star, that means it is not the direction is not significant, polarity is not significant. We are dealing with the mean square value, the power delivered to the load, that is the conventional way of defining noise. So, we do not worry about the polarity. So, we just put a star over there. Likewise, if we talk about the noise as a current source, we put a double arrow up as well as down, so that we can signify it is not really important to mention the polarity or the direction of the noise current flow. We are just concerned with the mean square value. Now, if I talk about the power delivered to this 1 ohm load, once again we can use the same expression 1 upon t, 0 to t, the total signal, we can take the superposition of this, these are time domain signals, V n 1 t plus V n 2 t square by R. R is by definition here 1 ohm. So, this is what we get, and we can write this as V n 1 square t plus Vn 2 square t plus Vn 1 t Vn 2 t dt 0 to t. So, if I look at the first term and the second term, that is just Vn 1 square t dt 1 upon t 0 to t. So, that is just the mean square value of the first source. So, I can just replace this by Vn 1 square RMS. Likewise, the second term Vn 2 square t dt 1 upon t integrated over 0 to t is once again Vn 2 square RMS. Right. Now, if you look at the third term, it is something like a correlation between the two noise sources Vn 1 t times Vn 2 t dt, and the third term over here, as long as these two noise sources are independent, they are going to be uncorrelated, and as a result this product Vn 1 t Vn 2 t integrated over a long duration is going to lead to 0. Simplest example is, suppose my noise is having only two levels 1 and minus 1, equal probability, it is a either it can take a value 1 or minus 1, just a simplistic case. So, I am sampling at different time instances, and by with equal probability the two sources they can take 1 or minus 1 values. Overall, over a long duration, it is 50% probability that the noise can take plus 1 or minus 1 value. This is Vn 1 t and Vn 2 t. So, without going into detailed derivations and proof, I can say that if I multiply these two, they are uncorrelated. If I multiply these two and look at the overall signal, again it will have almost 50% probability of plus 1 and minus 1 value, and therefore, being summed over a sufficiently long duration, once again it will result in 0. This is a simplistic case. Of course, you can have any amplitude over here, it is not limited to plus 1 minus 1, it can have any intermediate amplitude, but the main point we want to convey is that if you are having two uncorrelated noise sources and you are multiplying them together, summing it up for a long duration, once again the resulting noise value, the signal over here, summed over a long duration, it will tend to 0. So, this correlation product, if you take the mean of this is something like taking the mean of Vn 1 t times Vn 2 t, that once again tends to 0 if we integrate it for a long duration. So, this becomes 0 and we are left with only the first two terms, which is the Vn 1 square RMS plus Vn 2 square RMS. That gives us the significance of defining the noise in terms of their mean square values. If we are dealing with two independent noise sources, we can add their mean square values. We do not need to worry about their time domain amplitude, we just care about the mean square noise produced by the first source, mean square noise produced by the second source, and we add the mean square, we add the power of the noise, we do not add the time domain amplitude of the noise. This is one of the important concepts related with the representation of noise in the circuits. Now, if I talk about the frequency domain characteristics, how do we define the frequency domain characteristics of noise? To do that, once again we have a noise source, we want to figure out what is the frequency domain characteristics of this noise source V and T. To do that, conceptually we can put a very sharp filter over here, say of bandwidth 1 hertz, center frequency is f naught, so some center frequency f naught and bandwidth 1 hertz. So, it will pass the signal only within this 1 hertz bandwidth centered around f naught, it will block all other components of the V and T, and then we supply it to the load, which is the 1 ohm load. All right. Now, if I once again plot the mean square value coming over here, that denotes the power delivered to this 1 ohm load when I am centering my filter at f naught. So, whatever amplitude V n square I get here, it is going to give me the power delivered to the 1 ohm load when the center frequency of this filter is at f naught. Now, I can keep changing this f naught, I can keep sweeping this f naught, and at different points I can calculate or I can find out what is the Vn square delivered to the load. And if I take very fine sections, ultimately it is going to give me smooth curve, some characteristics depending upon what is the signal source. So, here I am writing Vn square because this is the Vn square upon R, that is Vn square upon 1, which is essentially the power delivered to the 1 ohm load, and on the x axis we are sweeping the frequency. So, by joining these points using a smooth curve, I get the noise power spectral density. So, it is telling us how the mean square power of the noise delivered to the load varies with frequency, which frequency is having highest component. So, if the peak is over here, we say that at this frequency you have very high component of the noise. In some cases, as I said, there are two dominant forms or two very commonly encountered spectral densities of noise. One of them is white noise, where it is almost flat. So, this Vn square that we get is almost flat, whatever frequency you take, whether it is f naught or 2 f naught or 100 f naught, ideally the noise power that you get, it will be almost same at all these frequencies. So, it is a white noise. And remember, the way we have defined this Vn square is by passing it through a 1 Hertz filter. So, we are talking about power delivered in this 1 Hertz bandwidth. So, basically it is the RMS or the mean square value per Hertz. So, we define this as Vn square per Hertz. If you have to find out from a given noise power spectral density the total noise signal present in the particular source, we need to do is integrate this curve, right. So, I will just integrate this Vn square f df from 0 to infinity. So, basically I need to integrate all these sections and get the total mean square noise represented by the signal. That is going to give me the amplitude or the mean square, total mean square value of the noise source. So, this is the corresponding frequency domain representation, this is giving you the distribution of the mean square value of the noise across the frequency range of interest, and I have to find out total mean square value. I just need to integrate all these stripes and get the total mean square value. Another way, a common way of representing noise may be taking the square root along the y axis, rather than putting it at V square per Hertz, we can also represent it as volt per root Hertz. So, that is just changing the unit along the y axis, but this is the main definition. So, white noise is one commonly encountered spectrum. Another common spectrum is 1 upon f noise, where the noise increases with frequency, lower frequency. So, as we go towards lower and lower frequencies, the noise goes on increasing. So, this is 1 upon f noise, which is also very commonly encountered in circuits. Now, let us see how do we represent noise in the circuits. So, starting with a resistor. So, what we have seen is that, as per our discussion towards the end of the last class, we have seen that the equivalent noise voltage produced by a resistor, that can be modeled as a white noise source. So, the spectrum of the noise source produced by the resistor is flat, it is having equal magnitude at all frequencies. So, it is a white noise, and the power spectral density can be just denoted as 4 kTr. It is proportional to R, it is proportional to the temperature, and we just discussed the physical mechanism behind it briefly. Larger is the temperature, larger is the thermal fluctuation of the carriers in the resistor, and likewise if larger is the R, once again more scattering and more random fluctuation in the trajectory, leading to more noise voltage. So, this is the magnitude of the noise spectrum density. So, what we can say is this level, the magnitude Vn square per Hertz will be 4 kTr. And if I have to find out that, okay, before this resistor, if you put say a filter, suppose I put an ideal filter of bandwidth B, this is the bandwidth B, and I want to see that here what is the noise power this is going to pass. So, once again I have to see, I have to look at the spectrum, the bandwidth is located here. So, the noise only in this region will be able to pass, others are getting blocked. So, this the out of band noise is not passed, only the bandwidth which is accepted or passed by the circuit, that is getting communicated to the output node. We can also represent the noise of the resistor in terms of an equivalent current source. Just by taking the Thevenin equivalent, I can write down the equivalent noise current source produced by the resistor, that is 4 kT upon R, right. So, this is the equivalent noise current source produced by this resistor of value R, because if you multiply this with R square, remember this is the I n square, this is I n square. So, this is the mean square value of the noise, this is the mean square voltage. So, we have to multiply this 4 kT upon R with R square to get the resulting voltage, which is same as 4 kT R. And another point to remember is that this is not the mean square value as it is the noise power spectral density, that is it is denoting the magnitude of this curve, means what is the noise power spectral density. You have to integrate over a desired frequency range to find out what is the total mean square power delivered by this source to a particular load. So, once we are comfortable with the noise definition and representation of noise in a resistor, we can draw an analogy and define the noise sources in a MOSFET. So, just like a resistor, when the MOSFET is on, it is in saturation region, it is having a current flowing through the drain to source, and if I talk about the small signal current, that is proportional to the Gm. So, effectively the transistor is having some effective on resistance in the channel proportional to Gm. So, we can say the effective noise current source I n square channel is going to be defined a similar way, 4 kT some proportionality constant, say k naught times Gm. Generally this number for sufficiently long channel MOSFET is found to be 2 by 3. So, we get 8 by 3 kT gamma times Gm, where rest of the factors are constant, and you get basically 4 kT times gamma Gm, where gamma is around 2 by 3. So, this is the equivalent noise factor. So, we can represent it as 4 kT gamma Gm as the equivalent mean square noise for the MOSFET channel. So, this is similar to the MOSFET, similar to the resistance case, where this channel noise current is coming because of the resistive conduction path between the drain and source of the MOSFET. And just like the resistor, this is having the white spectrum. So, once again if I talk about this noise, this is again having a white spectrum, and the magnitude over here V n square per hertz is denoted by 4 kT gamma Gm. So, this is basically I n square. So, I n square RMS or mean square value. Another important noise source in MOSFET comes because of so called 1 upon f noise, which is slightly more involved to explain. So, that is represented as a voltage source in series with gate. Here the V n square or the mean square value, as I said, it is having a 1 upon f dependence on the frequency. This is a proportionality constant k, and then we have W L times C O x. Here the main mechanism that is involved in the production of this 1 upon f noise deals with the carrier flow across the channel. So, whenever we have electrons accelerating from say source to drain and you have a current flow, you have interaction between these accelerated carriers and the interface oxide, and there can be exchange of carrier between the oxide interface and the channel. So, because of electric field in the positive direction. You are having for an NMOS, for example, you are having a electric field from drain to the from the gate to the surface. Likewise, you have electric field from drain to the source. So, electrons definitely they have a strong positive velocity from source to drain because of the positive electric field. Likewise, they do have some gradient of motion or velocity in direction perpendicular to the gate, and there is a continuous trapping detrapping phenomena that can happen at the interface. So, interface is not perfect, you can have some dangling bond at the interface between the Si and the SiO2. So, inside at the between the SiO2 and Si, you can have certain bonds which are broken, they lead to dangling bond, and this becomes the trap of these electrons which are accelerated in the channel. So, there is continuous trapping detrapping phenomena of these carriers at this interface, and because of which we are having an effective change in the threshold voltage. So, remember how did we define threshold voltage? Threshold voltage concept came because of the accumulation of charge. So, we need certain maximum positive, certain minimum positive charge deposited on the metal gate to get sufficient number of negative charges inside the channel, so that the continuous channel is formed. So, suppose at a certain instance I already pump in some negative charges, they get trapped into the oxide over here, then you already have some trapped negative charges and you may require smaller positive charges to balance that total negative charge. Therefore, threshold voltage can reduce. So, threshold voltage can fluctuate whenever you are having this negative charges getting trapped detrapped from this oxide surface. So, for example, whenever you are trying to increase the gate voltage little bit, you expect that the channel charge will go up by proportional amount corresponding to Gm, but if you are ending up increasing the trapped charges, the electron charges over here, the increase in channel charge will not be so much, because some of the trapped negative charges they are compensating for the additional positive charge that you have put on the gate. Therefore, it will fluctuate from the desired value. So, there is a basic mechanism, but just in a hand waving argument without going to the deeper physics or derivation, we are just trying to state the basic mechanism that this is the main phenomena which results in the 1 upon f noise, and this 1 upon f noise characteristics is mainly resulting from this trapping detrapping process. If you are going towards lower frequencies, this trapping detrapping process is able to track the low frequency signal much more easily. So, if you are changing the gate voltage slowly, this trapping detrapping phenomena is much slower, and therefore, it is able to track the changing gate voltage in a much better fashion, and it is able to introduce more noise. Whereas, if the signal at the gate is changing much faster, as compared to that, this trapping detrapping phenomena is slower. So, that it is not overlapping with the frequency, or is not really aligned with the frequency of the signal. So, this is shifting at lower frequency. So, lower is the frequency, larger is this trapping overall integrated trapping detrapping phenomena. So, if I want to find out total charge integrated because of this trapping detrapping phenomena, it will increase if we integrate it for a longer time or a longer duration. That means, the corresponding frequency spectrum is lower. If I observe this noise for a longer duration, the amplitude will be integrated. This trap detap charge integrated over a long time will give me larger change in the threshold voltage, larger change in the charge accumulated, and therefore, this 1 upon f noise comes into picture. Other term we look at is COX. What is the COX? The COX is epsilon OX upon TOX. So, this also comes because of this charge trapping detrapping. So, if you have a thicker COX and then you are trapping some additional charges over here, because of that the electric field that is produced, integrating the electric field produced because of this negative charges, say it will produce a larger voltage drop if I increase this TOX. So, the overall voltage drop produced across this oxide will be larger if the oxide thickness is larger, because if you are just integrating the Gauss using Gauss law, you can get electric field produced by this additional trapped charges. If the TOX is larger, E times TOX is the delta VOX, there is a small change in the electric field produced across the oxide is also going to be larger. Therefore, larger is the TOX, larger is the integrated noise or the 1 upon f noise. And the other factor, that is W times L, it denotes the total cross section area of the MOSFET. Basically, what happens is, because there is so much trapping detrapping phenomena happening all across this oxide interface, if you increase the area of the gate, on an average these trapping retrapping phenomena will cancel out, because you have a large area, right. So, if you are integrating or summing up all these trapping retrapping phenomena over a large area, it will become closer and closer to 0, just like the phenomena of summing noise at different instances. So, here we are not summing the noise at different instances, but we are summing up this trapping retrapping across a large area. Larger is the area, more is the probability of that total summation approaching 0, because in this entire gate area you are having some trapping retrapping going on. So, larger is the area across which you are integrating, smaller is the mean value. So, just like in case of the random signal, we integrated over a long duration, and then those plus minus 1 will tend to 0 if I sum it up for a long time. Just like flipping a coin, if you are flipping it up or down, if you do it for a large duration or large number of tries, the mean value will be 50% up, 50% down. Likewise, here if I assume that there is trapping retrapping going on, if you sum it up over a large area, the mean value tends to 0, because it is plus minus, same phenomena. Rather than averaging in time domain, we are averaging over area, and therefore, we have WL coming into picture. So, this is the expression for the noise spectral density coming because of the 1 upon f noise Vn square, which is represented at the gate. And once again, we are getting some important information regarding the device. So, larger W and L is able to minimize the 1 upon f noise, and therefore, it may be advantageous in certain cases wherever the 1 upon f noise is becoming critical. We see that larger W and L can help us minimize that. Likewise, here if we look at the channel noise, it seems like larger GM is giving me larger channel current, but it may not be the right picture or may not be the most effective way of observing this noise. More effective way may be to represent or capture the effect of this channel noise current into an effective gate voltage, noise voltage. So, this is something similar to the GM VGS current that we get from drain to source, right. In the MOSFET model, we anyway have GM VGS flowing from drain to source. So, for applied gate to source voltage VGS, we have a GM VGS flowing between drain and source, and for a given VGS, the small signal current flowing from drain to source happen to be GM times VGS. Now, I have this noise channel current defined in parallel with the channel conductance, that is 4 kT gamma GM, and how can I represent it in form of an equivalent noise voltage at the gate? So, I can just divide this by GM square, because GM square times this noise equivalent noise voltage is going to give me the current. So, I can look at it, I can represent. So, this is the 1 upon f noise, this is the channel noise f channel. So, in order to represent the f channel, provided my source is grounded, assuming that the source is grounded, I can represent it in the form of Vn channel by dividing this mean square current value 4 kT gamma Gm by Gm square. Remember, this is a mean square value. So, if I have to represent it in terms of a gate voltage, it will be divided by Gm square. So, Vnch will be 4 kT gamma upon Gm. So, the equivalent noise voltage referred to the gate can be represented as 4 kT gamma Gm. So, in circuits generally it may be important to look at the input referred noise, that if you are applying a signal at a particular terminal, say between the gate and source, so as compared to the applied signal, what is the mean square value of the noise over here. So, actually the noise may be present because of the channel current flow, but I can refer it to the input, I can represent it as an equivalent noise voltage at the input, and that is convenient to compare with the applied input signal. So, we call it input referred noise, and this is coming to be 4 kT upon 4 kT gamma upon Gm. So, it seems that here if I look at this form, increasing Gm may help us in reducing the input referred noise. So, this may not be giving us the right picture, because when we talk about noise, we always have to talk about noise in terms or in relation with the signal. So, we will see that a larger Gm also has a role in amplifying signal. When we try to have a larger amplification, we need larger Gm. So, Gm plays an important role in amplifying the input signal. So, if we apply an input signal over here, V in, the small signal current that we get is Gm times V in. So, if I talk about the mean square, it is Gm square times V in square, right. So, the output signal square is proportional to Gm square times V in square, whereas the noise is proportional to Gm. Therefore, relative to the noise, the signal is more amplified. So, Gm is playing an important role in amplifying the signal. Whatever weak signal is present over here, it is able to amplify that signal by the factor of Gm square, V in square times Gm square. Therefore, although it may look like that the channel current noise is 4 kT gamma Gm and creating a larger Gm may mess up with my noise, but in fact, if I refer it back to the input, if I compare it with the input signal, then it seems like no, not really, means a larger Gm may help to reduce the input referred noise at the gate. That is another very important concept while dealing with circuits, more complicated circuits where you have bunch of transistors inside the circuit. We try to derive what is the equivalent input referred noise of that circuit, so that it can be compared with the input signal. So, now if I want to complete the small signal model that we earlier arrived at, including the parasitic capacitances, I can add my noise sources over here. That is, this is the Vn square 1 upon f noise coming in series with the gate, and you also have a channel current noise, which is, you can call it Vn square channel, which is coming between drain and source. So, this basically completes our MOSFET model. We have incorporated the effect of two noise mechanisms in the MOSFET, that is 1 upon f noise and the channel noise. And now we have some hint also that while analyzing the circuits, what do we need to do to the channel current noise? We can refer it to the input and then solve for input referred noise. That is the main step we are going to follow while solving some of our circuits using this concept. So, thanks a lot.